This is lecture 7 of Computer Science 47 course, Computer Organization. We'll be starting on the memory usage through the assembly programs. So we have like 3 parts of the memory usage to discuss. So today's like I think most simplest part, memory usage 1. And what we'll do, we'll go and talk about the registers access in the through the assembly program. Okay, so in just to note, uh, from the high level programs, usually it is not possible to access registers directly, with exception of course like language like C provides some variable type which explicitly use registers in place of like normal variable, which is always associated with some memory address. We can access registers in the C language, but also not very common usage, by the way. It is more like whoever is doing programming at the very system level where performance is needed. In that programming domain, people usually use that feature of C language. Now, these registers, if you recall, like in the lecture 1 and 2, we started discussing about different components of a computing system, and we have seen that there is a register file which we can uh, imagine as a very fast memory residing inside a processor. Okay, but quantity is very limited. For the processor MIPS, we'll see we have only 32 such storage element, which we call a register inside the CPU, central processing unit. So CPU has one control unit, one register file, and another ALU. These 3 major components, they together build up a microprocessor. So for the MIPS, we have 32 register, and in assembly language, we access those register directly inside a program. We use them frequently as needed. We usually try to avoid kind of use like a concept of high level variable, which is nothing but, we'll see later in the next lecture and so, which is nothing but a memory location. We always need to read from it and then change the value inside and then write to it. So it's a time consuming process. So in the assembly level, we want to use the registers as much as possible in our program. Again, as I said, MIPS provides user accessible temporary storage. They resides inside the CPU, inside the processor, but they are limited in number but very fast access. Each of the register is 32-bit long, assuming we are talking about 32-bit MIPS. If it was 64-bit MIPS, then your register would have 64-bit in it. And this 32 groups of register, this very special storage element inside the processor, is called a register file. So remember this diagram, that's what I was talking about. We have the processor has 3 major components: your control unit, register file, and ALU. So we will be seeing this register file and couple of other special register like program counter, instruction register, not really in the programming sense because we cannot access instruction register directly, we cannot manipulate it. This content of the instruction register is updated when we fetch an instruction from the main memory. Okay, program counter also we cannot manipulate it directly, but indirectly of course we can do the change in program counter. The one we can access is the register file. The 32 register. Strictly speaking, not really all the 32 register. We'll discuss about that, but let's assume for time being we access register file, we can write data into it, and we can read back the data from it directly through your assembly programming. So these 32 are the general purpose registers, and there are some name associated with each register, and of course there are numbers. We can refer them through a number, like register 0, register 1, 2, 3, etc., till 31, so 32. But also we have given the name to it so that it is easy to remember them, especially their usage purpose. Okay, especially their usage purpose. Now just to note, okay, the usage purpose, which is like the third column, it says except for these 0, we can use them from our program, in our program for any purpose. Okay, then this third column, what it says, it is a suggested usage and the convention of the usage of those registers. Convention of usage of those registers. For example, A0 to A3, they said, okay, we will use it for passing arguments into the function, whatever the function as a notion we can implement. We'll see in further lecture what we mean by a function and how it can be implemented in assembly language. Remember, macro instantiation is not a function call, right? So function is something different, completely different thing. It looks different. It kind of, when you write, it is more complicated to write inside assembly, not unlike your high level program when you can write. The function is usually you go and first write some methods or function in the high level program and then assemble different programs together to make a software program, right? Assembly is a bit different, so we need to be very careful when we talk about the function in down the lecture. I think 4 or 5 lecture down the line. Be carefully attentive to that lecture. Okay, you need to be very clear about that concept. But anyway, nonetheless, let's say our usage, we wanted a suggestion that A0 to A3, these 4 registers will be used for the argument passing to a function. It does not necessarily mean you cannot use them for other purpose. You can store them, you can retrieve the value at any point of time. No one is going to prevent you to do that. Okay, like neither assembler will give any warning or error message, neither your processor will complain, stuff like that. All right, like T0 to T7 is its suggested usage is as a temporary register. What is meant by temporary? It will be clear in function. Again, that lecture related to the function implementation in assembly. But let's say the target usage suggested is a temporaries, but we can use it for any purpose as we need, as we want. Okay, so no one is preventing you to write on any of these register except register 0. You can write onto this 0 some value. Assembler won't complain, but what you will immediately realize that your processor is not changing the value inside this register 0. This 0 register content is always 0, always remains 0. You cannot write onto it any other value. Okay, so this is the only exception where you cannot write anything, but again your assembler won't complain. Only that when you are running your program, you will see processor is refusing to write onto this. Means it don't bail out or it don't crash or anything. You will just see simply the 0, that register 0 value is not changing. It is just remaining at constant 0. So that's the suggested usage of the constant value 0. Okay, and the fourth column is again more related to function implementation. We won't be necessarily dealing that in this lecture. We'll be focusing on how we can write into these registers and retrieve the value from the registers. But this is a good reference. Okay, so whether these values of this register are preserved by through a function call or not, and again these are assumptions. Okay, so we assume, for example, 80 is not preserved, v0 v1 is not preserved, like t0 is not preserved, s0 s1 is preserved. So these are our programming convention. You may not need to follow that convention, but the danger of not following that convention is that when you are writing a module and you are integrating with some other part of the software which is being written by other person, then there can be this convention conflict. Okay, so that's why everybody writing assembly in MIPS follows this convention. Okay, follows the usage and follows the preservation, especially the preservation across a function call. Okay, so we'll talk more about this function call and preservation of the value, etc., later in the function lecture again. Okay, one thing to note, in your first page of this assembly, your textbook, that green page which talks about the MIPS list of MIPS instruction and stuff like that, it has this table exactly like that, except that book assumes the A0 to A3 the value are not preserved across the call, but in this class we will assume it is preserved. Like so, that's why I kind of overwritten that part with an yes. So throughout this semester, throughout this class, we will assume A0 to A3 the value is preserved across a function call. Okay, if you don't assume it, your project implementation is not going to work. Okay, so you must assume this part for this class, this semester, which is different than what your textbook assumes. All right, now we have these 32 registers, we have their number in it. These are, we can access it, write it, etc., etc. What are the different usage? Let's see. The constant value 0, as I said, the 0 I cannot write into it, it remains constant. AT is assembler temporaries. So AT is a register which is used by the assembler for pseudo instruction expansion. Okay, so often if you are using a pseudo instruction, after the assembling is done, you can look at your pseudo instruction has been expanded to two or more instructions, and that involves AT. So that means if you are using AT for your own purpose, store something and etc., etc., it can and will get overwritten if you are using a pseudo instruction. So it's better to avoid using AT in your program. Okay, let the assembler use it, solely use it, solely access it, and do whatever it shows. So assembler don't interfere with the other registers. Assembler uses this, only this register number 1, which is referred as $AT. Don't use it in your program. The V0 to V1 is a function call result and expression evaluation. We'll talk about more in the function call section. A0 to A3 is the arguments to be passed to the function implementation. We'll talk more about that later. Temporaries T0 to T7, 8 temporaries. Their value is not preserved across the function call, but you can use it. The only assumption is that if you are using and storing some value inside it, and then you call a function, it is not guaranteed that these values inside T0 to T7 will be preserved after the call is done. Okay. However, the safe temporaries S0 to S7, this register, it is guaranteed by convention, by software convention, that if you are storing some value with from like S0 to S7, this T8 register, you call some function, it is guaranteed that after that function is done, the value will remain as it is inside those 8 registers. We have some more temporaries, like 2 more, T8 and T9. These are same as this. So we have total like 10 temporaries which value is not preserved across the function call. Now K0, K1 is reserved for the OS kernel. So this is more important for the compiler, so that compiler don't produce an assembler code which uses K0, K1, especially for the user program. Like, so if it is a part of the OS kernel program compilation, they are allowed to use K0, K1. But if it is an user program which is not a part of the OS kernel, then they are not going to use K0, K1. But in this class, since we won't be dealing with the operating system around us, we'll be directly doing an assembly program and like run it directly on a MIPS processor, of course in a simulation environment. We can use it safely, okay, K0, K1. But I don't think in whole semester there would be any such programming problem that actually you need to use that register. You have a lot of register in your hand, more than enough, okay. Now GP, SP, FP and RA, these 4 registers, you can write and read it, but they are used for some very special purpose. We'll talk about these in next lectures, successive 2 more lectures, about the global pointer, stack pointer, frame pointer. Frame pointer will come in respect to the function implementation again, and return address also related to the function implementation. Okay, so these 4 register I would suggest not to use it in your program. Don't manipulate it, unless of course there would be some special scenarios, special operations where you need to use them. But in general, just don't use it as a general purpose register, and I'm pretty sure you'll be good enough with the rest of the registers. So what is our restriction? So 0 we cannot write, 80 we need to avoid, 2 registers we need to avoid, last 4 GP, SP, FP, RA. So 2 plus 4, 6 registers we need to avoid. K0, K1, let's say they can be used, may not be used, you don't need to. But if you need really in a bad position that you have exhausted all other registers on your hand, yeah, go for it. But okay, it's kind of an yellow zone, like you don't need to. Okay, so 4 plus 2, 6 plus 8. So out of 32 registers, 8 register has some kind of restriction on the usage for the user program. So we are dealing with 24 register, and I'm saying 24 register is sufficient, at least for this class purpose, to implement any program, whatever program we are going to implement. And next point is this. So as you have seen, lot of this usage assumption are around function call, like V0, V1, A0, A3, and also these temporaries, whether they saved or not. There's something around the frame pointer, return address, they are also related to the function call. So function call is a real complicated concept, okay, and also is a very important concept. So many assumptions are around this function implementation. So when we come to that point, please pay attention. Okay. Now last but not the least, there are 3 more register we need to talk about, which are special purpose register. One is program counter, and we won't be talking about the instruction registers because we cannot access them directly. It is just an after instruction fetch from the memory, that instruction register get updated. We'll discuss this program counter and high low. Okay, high and low. So program counter, we all understand, it is basically pointing to the, it is containing the address. That is what I mean by pointing to the next instruction. It is containing the address of the instruction to be fetched next. Okay, so that's the program counter value, and these value are changed with kind of when you are introducing a jump or branch in your program. We'll see in the programming detail of the assembly language, we manipulate this program counter, but there is no instruction that I say, okay, go and write into program counter. No such instruction. Okay, but we kind of indirectly manipulate program counter. Now high and low are two special purpose register, which also we cannot read and write directly, but we can do indirectly read and write. What does it mean is that we cannot access these two register high and low with the similar way that we used to access these other registers, other 32 registers. Okay, so we cannot access in the same way. MIPS has provided some special instruction to access values of high and low, and also we can write them through some special functions. So that's what they are, special register, and it cannot be accessed through the general way or through the commands or instructions through which we access the general purpose registers. Okay. Now the purpose, what is the purpose of high and low? We'll see in the second half of our semester when we are about to learn binary multiplication and build a digital circuit of a binary multiplication. We'll see that result of 32-bit multiplication is 64-bit. Okay, result of 32-bit multiplication is 64-bit. So these two special registers are there to hold result of multiplication, number one. Okay. Number two, division operation gives two results. One is quotient and other is remainder. Okay. So division result into two, division operation results in two answer. One answer is quotient part, other is the remainder part. These two result goes into high and low register, and then we need to access them as our need. So these are two special purpose register.